Hi, welcome back. We have entered chapter 6 on recursion in SQL. Okay, well, let's not waste time and look at the first practical example of using the recursive common table expressions in SQL. Okay, and the first thing that we would like to do is to re-implement a good old friend, namely the generate series set returning function. Okay, so we've all used it many times to generate sample data for our assignments or for some sample tables during the course. As you know, generate series has the ability to generate a sequence of integers I between some starting value from and some ending value to inclusive. Okay, and then there's of course defined step width and so on. Well, we've just assumed the simple case here of a step width of 1. Right. Okay, so given two parameters from and to, we would have to generate this actually arbitrary long sequence of integers, and that's a job for with recursive. We would have a hard time to express this particular query without the with recursive common table construct. Okay, so what we would like to emit here is, of course, a one column table. That's what generate series would leave us with, right? It's a set returning function or a table generating function. That's what we would like to compute here. A table series with a single column I, all right? Well, I've prepared this already here. So this recursive common table expression will compute a one table series and it will have a single column I. In the post-processing query, we will then just dump the contents of the recursive table that we have computed. So not much post-processing going on here. It will be different in many of the applications that we look at. There will be more complicated post-processing, but well, generally you will find that post-processing can be regarded as very straightforward, even trivial in some cases. Sometimes it's just the identity function, as in this case. Okay, so we do know that at least the value from will be part of the generated series table. And that's what we do in the base case query, in the query Q0 that is evaluated only once, the part before the union, right? Before the union separator. Here's the union separator. We are still talking set semantics here. We will come to the union all variant in the next video. Okay, so to make sure that the from value is part of this series recursive table, well, we would just put it there. This is just a literal table with a single row and a single column that contains the integer value from. Right. Now we would enter and describe the recursive part here. This part will be iterated until it yields no row whatsoever. Okay. You see that this is indeed a self-referential or the recursive part of the query. We are referring to the table series here, which is just being defined by this query. All right, so indeed there is the self-reference. This is the recursive part of this query. When we evaluate this particular part the first time, the contents of the series table will be the contents of the result that Q0 left us with. So it's just the from value. It's a single row table with a single column. Of course, it has this particular schema, the series table, right? It's a single row table in which we will find the from value. We would then check that we have not exceeded our upper limit. We don't want to produce values larger than our upper limit 2. If we have not reached this particular upper limit, well, we would then use the value that we were provided with and would just 1 to it. This is the step width. This is the task that we are left with, namely generating the next larger value from the value that we were provided with. Okay, and that would be the result of this recursive part. So nothing special here. Just remember that this table here, this table will yield just the row that has been produced in the last iteration. In the first iteration, it will be the result of Q0. In the next iteration, it will be the result of the new rows that we have just produced. The new rows that we have just produced. Well, we've got from, and we have just generated from plus 1. Okay, so that indeed is a new row that we have just produced. Only this particular new row will be seen in the series table on the next iteration, which will help us, of course, to generate the value from plus 2 in a sense, and so on. All right. Of course, when our generated values exceed the upper limit, if they exceed the upper limit or reach the upper limit even, then, well, this query will yield no rows. Okay, so a value that we have generated in the I column that reaches the upper limit, well, it will be filtered away. It will be the only value available in the series table. This part of the query will yield no rows. This is the stopping criterion, and the evaluation will stop. Of course, the union semantics has led to an accumulation of the result. This would be found in the result of the first iteration would be found in the result of the second iteration, the result of the third iteration, and so forth. So all of this would have been collected and is now part of the final result that we can see here in the post-processing query. Just recall, while we are iterating, we only see the new rows that have been added in the last iteration. Okay, so now you could ask yourself, there's this particular stop predicate here, this filter predicate. This will not admit values that are equal to 2. So actually, will 2 be indeed be part of the final table? This is the question below here. And if it's not obvious to you, then, let's switch over to the terminal and see how the whole thing behaves. And we will find out whether 2, the upper limit, is indeed part of the final table. So this is just the query that you've seen on the slides. I've instantiated the from and to parameters with 1 and 10 here. Okay, so we want to generate the integers in the range between 1 and 10, 10 inclusive actually. Okay, this predicate appears to say that 10 inclusive is not possible, but if you evaluate this, okay, so then we get a single column table. That's the series table, right? It has a single column I, and it contains all the integers 1 to 10. It's even in the correct order, but of course, you know, there is no guarantee for any order here, right? So it's 10 rows. The 10 indeed has been also put into the result, and this is the answer to the question on the slide. Let's have a closer look at why this is. Why is the 10 included? Let's trace the evaluation and the contents of the series table over the course of the different iterations. Excuse me. So indeed, let's trace what happens in our with recursive common table expressions for the parameters from equal to 1 and 2 equal to 10, just like in the terminal over there. So let's trace the contents of table series. The contents of table series after we have evaluated Q0. Okay, so after we have evaluated Q0, there's a single row in the series table. We have put it there using this literal table expression, and from equals to 1 in our example. So indeed, Q0 yields a single column, single row table that just contains the 1 here. Okay, so this is being fed into the first iteration, of our recursive query. Right? So this first iteration will see this input result. Okay, it will check the 1 against our upper limit 10, which is still less. So that row would be admitted, and we would use it to generate the next value in the sequence, the 1 plus 1, the 2 value here. All right. And well, this is the result of the first recursive evaluation. It's a new row that we have not seen so far. It would not be thrown away. remember the set difference in the semantics of the recursive common table expression in the union variant. So this is a new row. It would be kept. You see, it would be added to the result here that that we accumulate over time to then generate the final result in the end. Okay, this table would be the input. Only this table would be the input to the next iteration of our recursive query, which would read this single row table, would generate a single row table containing a new row that would be kept. Okay, so it's added to the result. This would be fed into the next iteration, and so forth and so forth. In the ninth repetition of our recursive query, we would read a table that contains an I value of 9. From that, we would generate an I value of 10, right? This would be added to the overall result, okay, and it would then be fed into the 10th iteration of our recursive query. Okay, so now the predicate, this predicate. This predicate will not admit this particular row. Our recursive query part will generate 0 rows of results. Okay, no need to add 0 rows to the final result here, makes no difference. This is also the stopping criterion. If the evaluation of the iterative query yields the empty result, this is a stopping criterion. The whole while loop of our iterative query semantics is left, and well, what we are left with here is the accumulated result over all the iterations here, and you see that indeed the 10 found its way into the overall result as we expected and hoped for. Okay, so this is a trace of our homemade generate series function. So okay, so to really deepen, to solidify our understanding of the semantics of the recursive, let's switch over to the terminal once more and play with variations of our homemade generate series. There we are again. Right. So first, I have prepared a variant of this with recursive common table expression here that is somewhat akin to the slide, the tracing slide that you have just seen, where we could see the result, the contents of the series table after each iteration. Well, this query is almost like the query that we've seen above here, but it also in a second column. In a second column, it outputs all the rows that are seen in the series table after the evaluation, after the iteration of the recursive query has been performed. Okay, so what we output here is not only the column I, we will do that still, right? You can see that here. But we will also output a column that shows the contents of the series table after each iteration, even after the zeros iteration, after the iteration of the Q0 base case query. Okay, so we know that after the Q0b base case query has been evaluated, the series table only contains a 1. You see that I represent the contents of the table using arrays here. Okay, because I cannot have nested tables in SQL. Okay, so all right. So after the evaluation of Q0, the contents of the table would only, the series table is only this particular 1 here. Okay, then this would be one recursive evaluation of the query would see the 1 row series table. It would check the predicate here. It would generate the next I value. And it would also aggregate all the generated I values. It's only 1, but it would generate all the generated I values inside an array, just to show us the contents of the series table that is being produced in this query. As you can see, we produce Si plus 1 here, as expected, to have the ascending generate series sequence. And exactly this Si plus 1 is also aggregated here to show us, hey, this would be the contents of the series table after this query has been performed. And let's do that. And as you can see, oh indeed, this series table is always a single row table. After the first iteration, or the zeros iteration actually, when Q0 has done its job, it only contains the single one here. After the first iteration of the recursive part, it only contains the single 2 here. No accumulation is going on here in the series table, right? It only contains the value that has been produced in this very iteration, right? Of course, this final post-processing query sees the accumulation of all of these partial results, of the temporary results, so that it can present us with the entire sequence of values here. But in each iteration, in each individual iteration, the series table only contains the stuff that has been produced in the last iteration. Okay, right. Well, if we can implement with recursive like this, and we can simulate the behavior of with recursive like if we can simulate the behavior of generate series with this recursive common table expression, then we could just use our knowledge about writing user-defined functions and wrap a UDF wrapper around our new shiny homemade implementation of generate series. And I've done that below here, right? You see here I'm defining my function, my UDF, my generate series here. Okay. It has, of course, 2 parameters, the from and the to parameters. From the viewpoint of SQL, these are funny column names, so I have to include them in double quotes here. What I will return is, of course, a table of integers, right, in column I. This is a set returning function, just like the real built-in Big Brother in PostgreSQL. Then, of course, I would just use the from and the to parameters of our function to guide and stop the recursive computation in our recursive CTE. That would be the overall result, as we have discussed already. Yeah, and that would be the result of my overall function. So let's define that. Okay. And well, I could use this my generate series function just like any other set returning function, maybe just like the built-in generate series function in PostgreSQL. So let's generate some integers around the very important integer 1138. And there you go, from 1135 up to 1141. Here's 1138 among its friends. This is the result of our own homemade generate series function. Perfect. Okay, so to really drive home, to really solidify our understanding of the semantics of this recursive common table expression in the union variant, let's look at 2 more variations of our homemade generate series. 2 variations in which I try to trip the entire implementation of our generate series function, but will ultimately fail to do so. I think this can be enlightening when you think about the semantics of this generate series with the union variant. All right, so everything looks like the original homemade generate series, okay? But here in the recursive part, I'm adding another literal table of exactly 2 rows, and I'm computing the cross product. I'm computing the cross product between our recursive table and this 2-row literal table. I just call the integers in the 2 rows of this table, I call them delta. Everything else remains the same. Right, so if this table only contains a single row in each iteration, as we've mentioned already many times now, well, this Cartesian product here will contain 1 times 2, it will contain 2 rows. So we will iterate over 2 rows here, and we will generate 2 rows at this particular point. 2 rows. One of the rows will be the value as I. One of the rows will be the value as I plus 1. Look at the values of delta here. They are 0 and 1. Because the value as I plus 0 so just as I, is something that we have already accumulated during the process of the evaluation of this common CTE, it will be disregarded, right? So si plus 0, or just as I, is something that we have already seen, we've already produced as a result in the previous iteration of this recursive common table expression. It will thus be disregarded and removed from the overall result. Okay, the si plus 1 value, which we will also produce here, this is something we have not seen so far. It will be kept and it will be part of the overall result, and it will be fed into the next iteration of our recursive query here. Right, so I think thanks to the semantics of keeping only new stuff that we have not seen before and throwing stuff away that we have produced before, namely those si plus 0 values that we are producing here, the result should just stay the same. And indeed it does. Indeed it does. The semantics of the recursive common table expression with the union and the removal of results that we have seen before is leading to this unaltered result of our homemade generate series. Okay, and to really drive home the point that we are talking about set-based semantics here and duplicates are being removed, let's look at another variant of this convoluted query in which I again compute the Cartesian product with this 2-row table here. In this case, I just don't care about the contents of the table. I'm just interested in the multiplication of the rows here. Okay, as you can see, this will lead to a Cartesian product of 2 rows. 2 rows will be filtered here. 2 rows will be produced here, but both rows will be identical. Both rows will carry the value as I plus 1. We are talking set-based semantics here, right? This is the indicator for that. It's a recursive common CTE using union. Set-based semantics means duplicates are being removed. And again, we should be left with a 10-row result that looks exactly what we've seen so far in our homemade generate series. There you go. It's the same thing. Right. Okay, so please don't be thrown off the track. These two variants here, this variant and the delta variant here, they are just here in this particular file to encourage you to play with the semantics, the set-based semantics of the recursive common CTE within the union case. In this case, throwing away stuff that we've seen before. In this case, throwing away stuff that we've produced twice or more times. All right. So play with this. Try to trip it. Maybe you can. Maybe you are successful in tripping it. It really makes a difference once we enter the union all side of things. But this is something to be discussed in the upcoming video. See you then.